Hello Year 12 further mathematicians, I hope all of you are well. Today's title is Introduction to Bivariate Data, and just before I get started, I'd like to remind you to complete the RL 6.5 lesson. Well, I say lesson, I mean the RL 6.5 assignment. That was to do questions 1 and 2 from the revision worksheet. Having marked your topic assessments for discrete probability distributions and discrete random variables, I noticed that some of you were a bit rusty, and understandably so. And so I think it's useful to do a few revision questions every week. After today's lesson, I will set another task for you guys to do for next week. So question 3 and 4 to do from the same worksheet, but yeah, you will have to hand that in next week. Moving on to today's lesson, it's our first lesson on bivariate data. We're not going to cover too much, but we will cover some important things within bivariate data. So on this list of learning objectives, we're going to cover the first 3 today. So just understanding what bivariate data actually means and linking it to scatter diagrams and interpreting scatter diagrams as well. So bivariate data means data involving 2 variables. Of course, this means 2, and this is like saying variable. And here it says bivariate data is data involving 2 variables where each value of one variable is paired with a value of the other variable. So here it says bivariate or not. So we have 2 examples, and we're going to discuss whether these examples show bivariate data or they don't. So the first one is the table. It says the table below shows the land area and population of the countries of a world. So we have one variable here. Okay, the choice of color is perhaps not the best, but yeah, we have one variable here. We have another variable here. And crucially, these 2 values correspond to each other, and they're paired up by the fact that they have the same country. And it's the same for all the other pairs of values. They all represent or are linked to a particular country. And so this is an example of bivariate data. Just gonna show you here what I was talking about. They're paired up. So that's crucial. It's not just about having 2 variables, they have to pair up as well. So the second example says below are 2 lists of weather statistics. Highest recorded temperature in the home nations. So it's got the temperature for England, Wales, Scotland and Northern Ireland, and the rainfall in London by year. And then it's got a few rainfalls. So here we have one variable, here we have another variable. The temperature and rainfall, they're both variables. Having said that, these values are not paired up, because here it says England, which is a country, and here we have a year. And so they're not being paired up by the same country, as you can see here, for example. They're not both, these data points don't both represent the same thing. And so this is not an example of bivariate data. There are 2 variables, however, they're not being paired up. So types of bivariate data. We have 2 types of bivariate data. We're going to discuss the first one, which is known as random on non-random. So in this case, only one of the variables can be considered a random variable, and essentially you have one variable which is controlled and the other variable is measured. So the one which is controlled is obviously not random because someone is controlling it, and the other one which is being measured, we're not in control of it, we're going to measure it, and it is random. So here's an example. A horticulturist is investigating the yield of tomato plants when different levels of fertilizer are used. This data is bivariate. Why? Because let's just change the color first. Actually, here. Yeah, so the reason why this data is bivariate is because firstly, we have two variables, they're both being underlined using a blue pen. And what pairs them up is that the yield of tomato plants is related to an individual plant, and the levels of fertilizer being used, well, a level of fertilizer is being used on each plant. So each plant corresponds to a particular yield and a particular fertilizer amount. Additionally, we know that this level of fertilizer being used is being controlled by the horticulturist. This is being controlled. He or she is determining a certain amount of fertilizer to use and then investigating the results, measuring the yield of the tomato plants and seeing what differences emerge based on how much fertilizer is being used. So the level of fertilizer is not a random variable, the yield is a random variable. The second type of bivariate data is random on random. So in this case, both variables can be considered as random variables. Let's look at an example. So a sample of Year 13 students are taken and each student's height and weight is recorded. So height and weight are obviously the two variables. And unlike the previous example, we don't have a person controlling the amount of, for example, fertilizer being used. There's no one who's controlling the particular heights of individuals, the particular weights of individuals. You can't go out there to a group of Year 13 students and say, okay, I want someone who has a height of, let's just say a weight of 50 kg, 60 kg, 70 kg, 80 kg. It's random. You're not going to have these perfect intervals between the heights or the weights. So height and weight are both random variables, and this is an example of random on random bivariate data. So now we've learned what case A and B actually are, we're going to decide whether the data is random on non-random or random on random. I'm going to show you 3 different examples and then we're going to discuss whether it's case A or case B. So a random sample of trees is taken, the girth of the trunk is recorded along with the height of the tree. So maybe have a go yourself and in a few seconds I'll discuss what the answer is. So we can see that the second example has been slightly adjusted, and so she's still investigating the number of crabs in a particular area, but it says here she picks a sample of areas of 1 square meter, each of which is a multiple of 5 meters from the sea. So multiple of 5 meters from the sea, so distance is one of the variables, and of course number of crabs is another one. Although they haven't written it, it's clear that this is like an extension of the previous example. So number of crabs, distance, each they're tied together because they are linked with a particular area. And okay, is this random on random or random on non-random? So number of crabs is definitely a random variable. She can't control the number of crabs. Distance, however, as it says here, each of which is a multiple of 5 meters from the sea. So the first one is 5 meters, then it's 10 meters, then she's going to select 15 meters, 20 meters, and so on and so forth. So this is definitely being controlled, and so the distance is a non-random variable. So I'll write here random on non-random, and in brackets I'll write A for case A. Scatter diagram. So the most common visualization for bivariate data is a scatter diagram. Each point on the scatter diagram represents a single statistical unit which pairs the data. So for example, on the previous slide, our statistical unit was, for the first example, was a tree. For the second example and third example, our statistical unit was the area, which each distance and number of crabs were linked to. So here we have some other examples as well. Of course, we saw countries from our first example. Each axis is a scale representing one of the variables. So on our scatter diagram, one of the variables goes on the x-axis, the other one goes on the y-axis, and yeah. So now let's look at an example. So we have a scatter diagram here for a random on non-random case. So a horticulturist is investigating the yield of tomato plants when different levels of plant fertilizer are used. So firstly, our individual plants are going to be our statistical unit, and now we need to think about what goes on the x-axis and what goes on the y-axis. So if one of the variables is independent, then this should be plotted on the horizontal axis. So levels of fertilizer being used will go on the x-axis. Fertilizer used, milliliters, will go on the x-axis, and we're investigating the yield of tomato plants, and so this will go on the y-axis. Okay, so when the data is random or non-random, the data points will appear in distinct vertical lines based on the controlled treatment levels. So what that means is, because we're changing the level of fertilizer, chances are these are going up in a particular pattern. So we saw an example on a few slides ago where they said the distance is in multiples of 5. It's very likely that the levels of fertilizer being used is in multiples of 2 or 5 or another number. So here you can see vertical lines due to the fact that the x-axis has a variable which we are controlling, and when we control it, we want to use particular numbers which give a pattern. Of course, if it was a random variable, the level of fertilizer being used would be completely random, but it's not. We're controlling the level of fertilizer, and so we would like it to go up in a particular pattern. So here you can clearly see that there are vertical lines. Case B, so what do we do if we have a random on random case? If both variables are considered random variables, then it's not as clear as to what goes on the x-axis and what goes on the y-axis. However, it's what we do in this instance is we treat one as a function of the other. And so here we have an example. An ice cream seller records the average temperature along with the total sales for each day in August 2017. So in this example, what is a function of the other? In other words, which one affects the other? Well, generally speaking, we expect that the temperature will affect the sales of ice cream, because usually when the weather is very hot, we have more ice cream sales, and so we put temperature on the x-axis, and we would place ice cream sales on the y-axis. And as it says here, we are seeing ice cream sales as a function of temperature. The higher the temperature, or I should say the higher the temperature, the higher the ice cream sales. And as you can see here, there are no distinct vertical lines because we're not controlling the temperature, we're just recording the temperature, and then we're recording the ice cream sales as well. It's not controlled like the previous scatter diagrams where you saw those distinct vertical lines appearing. The scatter diagram appears as a data cloud, so you just have a bunch of data points scattered around each other. For each of the following contexts, which variable would you plot on the horizontal axis? So which would go on the x-axis? Pause this video and have a go at answering the questions, and I'll go through the answers in a sec. Okay, so I'm going to go through the answers now. So we have the marine biologist example from a few slides ago, where distance was one of the variables and number of crabs was the second variable. The statistical point is the particular area which each of these variables represent. So which one affects the other? Well, usually we would think that the distance from C has an effect on the number of crabs. I don't know much about crabs, but the closer you are to the sea, would you expect to see more crabs? You'd either expect to see more crabs or less crabs, and to be honest, I'm not the person to comment on that. So I don't know whether it will be a positive correlation or a negative correlation. However, the distance should have some sort of impact on the number of crabs. So the higher the distance, either the higher the number of crabs or the lower the number of crabs. Part B, a sample of Year 13 students are taken and each student's height and weight is recorded. So firstly, let me just rub off. So height and weight. Just underline it. Height and weight. So this is quite a difficult one. We need to think about which one affects the other one. Generally speaking, height doesn't really, we're all born with a certain height. We can't do much to change that, but we can change our weight. And I'd actually think of it like this. Height, the taller you are, the more you weigh. So height does impact weight, whereas with weight, the more you weigh, it doesn't necessarily mean you'll become a taller person or a shorter person. And so I would say that height impacts weight and weight doesn't really impact height. So I'll write height on the x-axis. As I said, it can impact weight. The higher you weigh, the taller you are, the more you will weigh. That is how I would do it. And part C, a sample of year 13 students are taken and each student's hand span and foot length is recorded. So here we have an example which they're both quite level in my opinion, hand span and foot length. So neither of them actually impact the other. And so I wanted to show you guys an example where neither variable appears to be the x-axis, or sorry, it's hard to say which variable will appear on the x-axis. And so if we have a situation like this, then we just go with the one which has been written first. So we have our two variables and it's not clear which should be on the x-axis. So because hand span is written first, we'll write hand span here. It's a bit like BIDMAS, where at times you have to perform the operation which appears first. So hand span, foot length, not entirely sure what the units are. Let's just say centimeters. Oops. So yeah, I thought it was important to show you guys an example where we don't actually know what goes on the x-axis. So interpreting scatter diagrams. So an outlier in a bivariate distribution is a data point which deviates from a typical pattern to a notable extent. You need to be able to recognize outliers in a scatter diagram by eye. So I'm sure you guys know what outliers are. And of course, we've done some work on outliers in maths, in normal maths. So here I would like you to circle. Actually, it's very difficult for you to do if you don't have a piece of paper in front of you. But I'd say identify the outliers on these four scatter diagrams. I'm going to ask you to pause this video so you can figure it out, and in a few seconds I'm going to go through the answers as to what I think are, or I guess which of these data points I think are outliers. So the first scatter diagram, the law of the data looks very close to the line. The one which it looks quite far away is this one. That's the only one I'd consider as an outlier, to be honest. The next one would be this one here, but look, that's still very close to the line. So as the outlier. Let's come on to the second one here. So here we can see a lot of data around this part of the graph. We have one obvious outlier. I'd also say, sorry, just rub off this working out. Yeah, so I'd also say that these ones, sorry, these points are also outliers. I was gonna say this one, but no, I'm not, because there are a lot of points which, yeah, but I'd say these three for me are outliers. The third scatter diagram, we have an outlier here, another one here, and two more up here. I think this one's probably the easiest one. The rest of the data is all in almost a straight line. I think the line of best fit for this one would go through, or at least be near, a lot of those points. Number 4, we have a lot of data points around this region, and so I'd actually say we have one outlier. That's it, because it's quite a weak correlation. Well, not a weak correlation. It's a you can see there is a negative correlation, but there's a lot of data around that region, and there's one which stands out, and that's down here. So yeah, I'd say there's one outlier on that fourth scatter diagram. So another thing you can do with scatter diagrams are you can check the suitability of a particular model. So for which of the following is a linear model suitable? Again, have a go at answering that question for these 4 graphs, and I'll go through the answer in a sec. So remember, linear model means can you draw a straight line through it? So we can for the first one. The line of best fit looks very close to a lot of those data points. For the second one, I'm not so sure. I would say no, because if we had to draw some sort of line of best fit, it would actually have to be a curve, which looks like that. And so I'll put a cross for this one. For the third scatter diagram, yes, aside from a few outliers, we can draw a line. For the fourth one, this one's probably the trickiest. Like, you might look at that and think, okay, how do you draw a line through that? There's a lot of data, and it's arranged in like an oval shape. However, they're all in kind of, the pattern is going in the same direction, which is a negative correlation. And so I would say a linear model is also suitable for the last one as well. So that is it for today's lesson. A lot of note taking and not a lot of questions, but it's the introduction to bivariate data. So it was really important for you guys to learn some of those key terms and look at the different cases of bivariate data which we have. Next week we're going to learn about correlation coefficients. And so yeah, please make sure you submit pictures of your notes from today's lesson. I hope you made a lot of good notes. And just a reminder to please complete the RL 6.5 task if you haven't already. And please also do the RL 7.5 task, which is due next week. Please make sure you submit pictures of today's lesson. I think some people have been slacking slightly, but a few of you have also been amazingly consistent. So keep it up, those of you who have been doing great, and hopefully the rest of you can reach that high level again. So yeah, take care everyone, and please make sure you ask me questions if you have any.